All right, welcome to 3.3, section 3.3, implicit differentiation and related rates. Basically, implicit differentiation is just the mathematical fluency side of this section. In other words, we're just doing symbolic equations and we're finding derivatives. Whereas the related rates is the application side of the section. Cool. Let's start with implicit differentiation. What even is implicit differentiation? Well, so far when we differentiated a function, remember that's the same thing as saying find the derivative of a function, we have had functions that are defined explicitly, like these. That is to say, the name of the function is on one side of the equal sign, like y or f of x in these two cases, and the other side of the equal sign tells you what to do with that x, with the independent variable, in order to find the function value. Okay? So we've learned how to find the derivative in the last few sections. Note that we differentiated both functions here. We did the same operation, but the notation's just different. Okay, so dy dx is one of the ways to say we differentiated y in terms of x, and over here f prime of x is just another way of saying we found the derivative of f of x in terms of x. Okay. So we're going to be using that dy dx notation in this section. It's because it helps a lot. All right. So let's consider the case where a function is not explicitly defined. That is, it's merely implied. An implicitly defined function. Okay, so we've got y is all mixed up with the x's over there. We still want to know how the implied function y is changing with respect to x. Okay, that is, we want to find dy dx, just like we did up above. One way we could do that is to solve the equation for y, and then it would be explicitly defined, and then we could differentiate just like we did in earlier sections. But that's not always possible. So let's use this simple example to see how to implicitly differentiate for when we do find more complicated functions that we can't write explicitly as y. So first, we assert that since both sides of the equal sign are of equal value, then their derivatives must also have equal value. So we differentiate both sides with respect to x. All right? So it's just like doing an operation. We're going to differentiate both sides. Or we could say, take d dx of both sides. All right. When we do that, on the left-hand side, we have the derivative of one term plus another term. So we can use the sum rule, right, and split it up. So now we have the d dx of yx plus the derivative of y in terms of x, and that's equal to 0 because the derivative of a constant is 0. All right, now that first guy, the d dx of yx, is a product. So we use the product rule. And remember, it's the first one, which is y, times the derivative of the second one, x, plus the second one, which is x, times the derivative of the first one, which is y. All right? And, oh gosh, look at this one. So then the next term, which was d dx of y, well, that's just the definition of what dy dx is. It's the derivative of y in terms of x. All right, so it's just another way to write dy dx. So that's what we've replaced d dx of y with. That's exactly what dy dx is. All right, I hope you get that part. Okay, now we replace y times d dx of x, right? What is d dx of x? Well, it's just the derivative of x, which is 1. So it's just y times 1, or y. The next term, again, we have d dx of y, which we know is dy dx. So we have x times dy dx, plus, there's that third term, which is dy dx already, and equal to 0. All right, now that we've done all the differentiating, we want to start to solve for dy dx, because remember, that's what we're trying to find. So here we just subtracted y from both sides. We took a dy dx out of both of those two terms on the left-hand side, and we divide both sides by that x plus 1 term. And now we have dy dx is equal to opposite y over x plus 1. Done! Isn't that fun? All right. That was a romping good time. All right, another example, you say? Sure. This time, let's find the derivative at a point. All right. Given the equation x squared plus y squared equals 25, A, find dy dx, and then B, evaluate the derivative at 4, 3, and 0, 5. So x squared plus y squared equals 25. Does that look familiar to you? It should. It is the equation, you're right, of a circle centered at 0, 0 with a radius of 5. There it is. So what does it mean to find dy dx? Well, it's the derivative of y with respect to x. It's the instantaneous rate of change of the y variable as the x variable changes. In other words, it's the slope of the tangent line, okay? So the tangent line at the point 4, 3, the point 4, 3 lies on that circle. If you plug in 4 and 3 into this equation, it makes it true. So we know it's on the circle. And then you see this red and white dashed line here. That's a tangent line. It touches the circle only at that point 4, 3. And finding dy dx at 4, 3 will tell us the slope of that tangent line. Isn't that cool? And obviously, the same is true for that point 0, 5, right? 0, 5 also lies on the circle, and dy dx at 0, 5 is going to give us the slope of the tangent line at that 0, 5 point. And hopefully, again, you remember what the slope of a horizontal line is. Let's see if it works. All right, so again, we're going to differentiate both sides, and we can use the sum and difference rule. Again, that separates the x squared plus y squared into the ddx of x squared plus ddx of y squared is equal to the derivative of 25. See if you can think of what that's going to be before I hit the button. All right, we're going to differentiate. Oh, good. Power of rule on the first term, right? ddx of x squared. All right, implicit differentiation on the second term. Okay, so it's the chain rule plus, the definition of what dy dx is. And then the rule that the derivative constant is a 0. And sure enough, you got 2x for the first term. The second term is 2y times dy dx. And then that equals 0. And now we just have to solve for dy dx. And there it is. So dy dx is equal to opposite x over y. What does that mean? It means that anywhere on the circle, you can choose any point on the circle, and that point, that xy point, is the slope of the tangent line at that xy point is equal to opposite x over y. So dy dx at 4, 3, which is that first point, is equal to negative 4/3. And can you see that slope? It makes sense that the slope is negative 4/3. It's a little bit steeper than a negative 1, right? It's a negative slope, and it's a little steeper than a 1. And dy dx at 0, 5 is opposite 0 over 5, or 0. And of course, hopefully you remember, the slope of the tangent line, or the slope of a horizontal line is 0, or it has no slope. All right, cool. Fun example, huh? All right, let's do another example of implicit differentiation. This one's a little tougher. All right, so if xy plus x squared y cubed equals minus 1 equals 0, find dy dx. Now that would be quite a chore to solve for y, so I'm glad we got this tool of implicit differentiation. Note that both xy and x squared y cubed are products, so we're going to use the product rule. All right, so here it is. We're going to differentiate both sides. So we start out, we have a sum, so we'll split that up into 3 pieces, and ddx of 0, of course, is just 0. So here's our 3 pieces, just like I said. So think about what the derivative in terms of x is of xy. I think we did this one before. It's a product, so it'll be the derivative of the first times the derivative of the second, plus the second times the derivative of the first. And keep in mind what's different about x and y since we're differentiating in terms of x. Same thing for this. We'll use the chain rule and the product rule here. What do you think ddx of negative 1 is? Good, it's 0. Good job. All right, let's see what we got. I'm going to use the sum and difference rule. All right, so here it is. Here's the product rule for that first term. First times the derivative of the second. So x times the derivative of y. And the derivative of y in terms of x is dy dx, right? Plus the second, which is y, times the derivative of the first, and the derivative of x is just 1. All right, now we're getting somewhere. We're skipping steps a little bit. All right, in the second term, it's the same thing. It's a product rule. It's the first x squared times the derivative of the second. And the derivative of the second is the ddx, right? The derivative in terms of x of y cubed. So first you take the derivative of the outside, which is 3y squared, times the derivative of the inside. And remember, the inside is y. We don't know what y is, but we know we'd have to take the derivative of it, and that's what dy dx is. All right? Plus the second times the derivative of the first, and that's that y cubed times 2x. Okay? Plus, you're right, ddx of -1 is 0 is equal to 0, because ddx of 0 is also 0. All right, so now we're here, and I think we just rewrote it. Okay, nice. All right, so x dy dx plus 3x squared y squared dy dx equals, and then they just took these terms that weren't related to dy dx over here to the right-hand side, because we're going to start solving for dy dx. And we took a dy dx out of both of those terms, so that we're left with x plus 3x squared y squared. So we just factored that dy dx out of both of those things. And same thing over here. And we divide both sides by this binomial, and we've got the solution. Dy dx is equal to this monstrosity over here. And you're done, right? It's getting easier each time. All right. Now this one's not quite as complex, but how are we even going to handle those radicals? I think you know. First, we rewrite it using exponents. Don't forget, square root of x is x to the 1/2. Square root of y is y to the 1/2. And then don't be shy about fractions. They're your friends. All right. So again, we differentiate both sides. Take the ddx of both sides, however you want to say it. And we've got a sum here, or actually a difference, so we'll be able to split that up into those two terms. And ddx of 16, you got it, is 0. All right, so here it is split up into the two terms. All right, we're taking, now we just have to find the derivative of each of those three things. And one of them for sure you know is 0. Okay, so we found the derivative of this guy, of the first guy, and it was 1/2 x to the -1/2. We just used the power rule there. The second one, it's the same thing, but we also have to multiply it times the derivative of the inside, which is dy dx, okay? And that equals 0. All right, so we just moved this term over to the right-hand side, and now we're going to divide by this guy so we can get dy dx all by itself, or solve for dy dx. And it is not pretty. We have x to the -1/2 power over y to the -1/2 power, so we can just switch places so that they're positive exponents, y to the 1/2 over x to the 1/2. And to make it nice and neat, fewer symbols, the better. And we have, so we write it as radicals, and we have y, square root of y over square root of x. Or if you really want to get simplified, right, we want to write it in as few symbols as possible, we can do a single radical with the fraction underneath it. So both are fine. All right, now we're getting to related rates. So we've got a spherical balloon. It's inflated by a continuous flow of air from an air compressor at a rate of 2 cubic inches per second. So how fast is the radius of the balloon growing when the radius is 3 inches? So the secret here is to realize what 2 cubic inches per second is talking about, okay? Well, hopefully you realize at this point, it's the volume of the balloon. All right. In fact, so now here they're spelling it out. We know that dV dt, right? So that's the change in the volume with respect to time, is 2 inches cubed per second. So we have the volume over the time, just like we have the volume over the time here. That's how you know you're doing it right. And we want to find dr dt, right? We want to know how fast is the radius growing when the radius is 3 inches. So we want dr dt at this time where r equals 3 inches. All right. So the formula for the volume is 4/3 pi r cubed. So that was implied that you know that, or you could look it up. Here's the equation. Now remember, they gave us dV dt. So if we differentiate with respect to time, This guy right here is going to be dv dt, right? Because it's d dt of v, which is dv dt. And over here we've got d dt of this mess, which the only variable over here is r. So that's going to give us a dr dt term over here. And that's what's related. Those two rates are related, and we're going to describe through implicit differentiation how the two rates are related. All right, so we get dv dt is equal to 4/3 pi is just a constant, so that can come out, and it's, and then it's the d dt of r cubed. I would have done an extra step here, sorry. And d dt of r cubed is 3r squared, right? That's the derivative of the outside, times the derivative of r. We don't know what r is. That's what implicit differentiation is saying. That's just equal to dr dt, okay? Because d dt of r is dr dt. All right, so now you can see how dv dt and dr dt are related. All right, so we can simplify by dividing out those 3's. And we get dv dt is related to dr dt by this term here, 4 pi r squared. Oh, 4 pi r squared. That's the surface area of a sphere. That's pretty cool. I'm sure we could play with that, but not right now. Okay. All right, so if we substitute dv dt, they gave us was 2, right? It was growing at a rate of 2 cubic inches per second or whatever. And we know that the point at which we want to calculate the dr dt is where r equals 3. So we plug that in, and we get 2 is 4 pi times 3 squared times dr dt. And now we're just going to solve for dr dt. All right, so 3 squared is 9 times 4 is 36, so that's 36 pi gets divided both sides, and we have 2 over 36 pi is dr dt, or we can punch it into a calculator, and we get dr dt is equal to 0.018 inches per second. So that's the rate at which the radius is growing when the balloon has a radius of 3 inches. Whew. That was a very interesting one. All right, let's do another related rates problem. We have two cars, car A and B, those are some funky trucks, are traveling toward the same intersection. And neither driver plans to stop. Car A is half mile from the intersection, moving east at 40 miles per hour. Car B is 0.75 miles from the intersection, moving south at 60 miles per hour. How fast is the distance between the two cars changing? And so they're at a 90-degree angle from each other, so it sounds like it's the hypotenuse that we're interested in. How fast is the hypotenuse changing? All right, so yeah, there it is. So we've got, from the figure, we've got s squared, that's the distance between the two trucks, okay? And that's equal to x squared plus y squared. And they told us how x squared, or how x and y are changing. That's the speed of each of the cars. Differentiating with respect to t, we get, because remember, we want to know ds dt. We want to know how fast the distance between them is changing with respect to time. So, boy, none of these three variables is t, right? So we're going to get a bunch of fun terms here. All right, so we take d dt of s squared is equal to d dt of x squared plus y squared, and of course we can separate those. Note, as x and y are decreasing, their velocities are negative. So x is the distance from, one of the cars is from the intersection, so it gets smaller and smaller, and y is the distance of the other car from the intersection. That's why it's going to get smaller and smaller. All right, so differentiating each one of those is going to be 2. So for instance, d dt of s squared is 2s times the derivative of the inside, because we're not differentiating with respect to s, right? But it's with respect to t. So we assume s is some function in terms of t. So we say whatever it is, it's times the derivative of s in terms of t. Same thing with those two guys. All right, so so we solve for ds dt simply by dividing both sides of the equation by 2s, and so the 2's all go away, And we have this mess right here. All right, so if you substitute in x is 0.75, dx dt is -60, y is 0.5. Again, these are the distances, right, that they gave us. The distance that one of the cars was from the intersection was 0.75 miles, and the other one was 0.5 miles. And the speed with which it was, that its distance was changing, right, was 60 miles per hour, and this one was 40 miles per hour. So that's how we know what dx dt is and what dy dt are. All right, and we know that, remember, s squared is equal to x squared plus y squared, so they solve for s. All right, and we plug in our x squared and y squared, so we know what s is initially, right, when the cars are 0.75 and 0.5 miles away from the intersection. So this is the initial s that we're looking at. All right, so we can plug that in. All right, so we find that ds dt, remember it was that mess up on top over s, I believe. Oh good, they rewrote it for us, that's nice. So x times dx dt, so that 0.75 times -60 plus y, which is 0.5 times -40 all over 0.9, yada yada yada, and we get -72.2 miles per hour. So that is how fast they're approaching each other. The distance between the cars is decreasing at a rate of approximately 72.2 miles per hour. So it's negative, so that's why, which makes sense because they're getting closer and closer, so their distance is decreasing. Whew. Phew, that was a lot. My head kind of hurts, but it might be the smoke. All right, go do your homework. Actually, first, let's meet in Zoom and we'll do some of these examples. Can't wait to see you there.